Come on in, everyone. We've still got a few more minutes before class starts. Feel free to ask me any questions. I'm sort of multitasking here, so might be a little inattentive, but hopefully I'll catch up soon. Still got about another minute left. Again, feel free to ask me questions. Oh, great. All right. Looks like it's time to get cracking, and my other stuff I'm working on is not working out. Let me see what happened real quick with that. There I am. There I am. Okay, so this did work. That's good, at least. See if that's working. Okay, looks like that's all working. All right, does anybody have any questions before we get started? Oh, good. A bunch more people just jumped in. All right, so last time we finished chapter 3. Haven't had anybody ask any questions, so I'm moving on. Chapter 4 is about Newton's laws of motion. And just to get on the soapbox here a little bit and teach you something that I didn't learn when I went through college, and it actually cost me. So when you're going through a course like this one, for instance, and there's a whole chapter called Newton's laws, uh, I would say a good rule of thumb when you encounter something like that, a whole chapter named, after some particular law, then I would advise you to commit that to memory. In other words, take those laws, commit the Newton's first law of motion to memory verbatim, do it again for Newton's second law, do it again for Newton's third law, because that's how many of them are, and keep that current the whole semester or the whole 2 years or the whole 2 semesters, or 3 if you end up taking a 3 semester course like this. I would say the same thing with like when we covered gravity. There was Newton's law of gravity, and then there was Kepler's three laws of planetary motion. The planets sweep out equal elliptical areas with the sun at one focal point. The planets sweep out equal areas in equal time, and the cube of the semi-major, or excuse me, the square of the period is proportional to the cube of the semi-major axis. Those are all laws as well, so I would commit those to memory. The reason being is a lot of times instructors give you what they think is a really freebie because they expect you to know that. So it wouldn't be unreasonable for me, to have an online or face-to-face test, say a midterm or something, and I ask you, state Newton's laws of motion, or state Newton's second law of motion, or state Newton's third law of motion, or I might have a whole list of various laws of physics and then a whole list of various names of laws of physics, and then you match them. So you need to know, Newton's law, first law of motion, Newton's second law of motion, Newton's third law of motion, Kepler's first law of motion, Kepler's second law of motion, Kepler's third law of motion, all that kind of stuff. I literally had this happen to me my first semester in grad school. I was taking a tough class, graduate electricity and magnetism, and right off the bat, the very first question was state Maxwell's equations and their boundary conditions. And I mean, that's something we literally covered every day. It was a chapter called Maxwell's equations, and that was supposed to be basically free 15 points, and I hadn't committed to memory, so I didn't get it. So make sure you guys do that. I will also take the time to tell you, for instance, in 242, not only do I expect my students to know Kepler's laws and Newton's laws of motion, I also expect them to know all the forms of the second law of thermodynamics. I expect them to know the first law of thermodynamics. I expect them to know the zeroth law of thermodynamics and the third law of thermodynamics. So just keep that in mind. Hopefully that'll help you. So with that being said, I want to go on to chapter 4, which, like I said, is about Newton's laws of motion. And to do that, I want you guys to have some understanding of what happened, how it happened. And I also like to tell a little bit of history because not everybody's interested in physics, science, engineering, that sort of thing. So sometimes they get a little bit more joy out of the history aspect. So Newton, which we'll talk about later, is a bit of a weird bug. But he did say, if I have seen further than others, is only because I stood on the shoulders of giants, which sounds like a really humble thing for someone like Newton to say. And if you know anything historically about Newton, it's probably that he was not extremely humble. In fact, he bragged at the ripe old age of his upper 70s, if I remember correctly, that one, he bragged about being a virgin at the ripe old age of 79. Uh, two, he often bragged about his abilities to do things. He'd often just say, "Well, I've already proven that, no problem," that sort of thing. So he's a very, very confident person. And it's sort of like, let's take, a modern day model or something like that. When a modern day really beautiful model says, I'm beautiful, that could be seen as arrogance. But if it's true and monumentally everybody around the world is paying money for her to do stuff or him to do stuff, then there's actually some truth to it. So it's not necessarily arrogance. So there's a little bit of problem with that with regards to Newton because he, with the exception of possibly Einstein and Aristotle, Newton was one of the highest class brains we've ever had in our species. So it is pretty amazing. Now, what he was referring to, if you want to take the humble side of that comment, was specifically that, for instance, Newton's first law of motion, which I'll state, but I want you to copy it verbatim from your book. But I'm going to state it the way I do it, which is an object in motion tends to stay in that state of motion unless acted upon by a net external force. That's my version of Newton's first law. But Newton would have recognized that as what Galileo had already discovered. So Galileo discovered what we call Galileo's law of inertia, and that is in fact the same thing. I also was fortunate enough to see a Michelangelo presentation in Salt Lake City when it was traveling around and happened to be at the Science Center in Salt Lake City. And I got to see in his notes, and sure enough, Leonardo da Vinci said, "For it is obvious that if a eagle were to push down on the wind with a force of 50 pounds, then the wind would respond by pushing back up on the eagle with a force of 50 pounds. There's a case where clearly Leonardo da Vinci knew Newton's third law of motion. So that's what we mean when we say if Newton is seen further than others, it's only because he stood on the shoulders of giants. The part that Newton completely got right was, and on his own, was Newton's second law. And largely the first law and the third law were built by Galileo and common sense and a little bit of everybody. What Newton did was give us a whole paradigm, a whole way of thinking about science and a way of solving problems. If you look at Principia is really, it's like that thick and it's just packed full, written in Latin, packed full with him solving problems using basic geometry. And the reason why is because one, he was a brilliant geometer, and two, he didn't have access to sine and cosine and tangent like we do in calculators. So he had to do a lot of things by hand, or he'd have to do long, tedious calculations to determine, sines and cosines and stuff of that sort. So that's pretty interesting all by itself. I will tell you that when he made that statement, he was in the presence of Robert Hooke, who you'll learn about later, according to Hooke's law. At that time, Newton was giving a speech in front of the Royal Society. The leader of the Royal Society at that time, the president, was one Robert Hooke. And Robert Hooke was one of the many, many, many uh, uh, enemies that Newton had. He had very specific enemies, and this one was largely for good reason. The good reason being that Haley once asked Robert Hooke, "I wonder what kind of orbits you could get for an object orbiting around something that had an attractive force that goes like 1 over r squared." And Robert Hooke said, "Oh yes, I've done this before. I know exactly what this is. I'll bring it to you." Well, he never showed up, never brought the information. Haley went to him on a couple occasions. He never brought it. He said, "That's never mind. I'll just do it. I'll just do it again." And he never redid it. He never turned it in or anything like that. So Haley, on the order of a year later, asked Newton the same thing, and Newton said more or less the same thing. Yeah, yeah, I did that. I proved that some time ago. And he went looking for it, couldn't find it. He said, "Well, hold on, I'll just redo it." And then, like 2 days later, Haley got a letter from Newton saying, showing him the actual work. And what Newton had done was proven that 1 over r squared law, in fact, is only one of two forces that can create a closed orbit, and that the orbits from such forces are conic sections specifically. They can be circles, they can be ellipses, they can be parabolas, or they can be uh, uh, hyperbolas, and that's basically it. So Newton did, of course, do that and was able to show that. Well, Robert Hooke went the rest of his life swearing that Newton had stole his work, but Robert Hooke never came up with it. And then later, when a problem was suggested by another mathematician, everybody knows Newton ended up solving that, and neither Leibniz nor Robert Hooke did. That's another reason that we think probably Leibniz did not independently invent calculus. He probably got a really big hint from someone who happened to visit Newton and then came back and visit Leibniz. Leibniz also became one of Newton's enemies, so we've got that. All right, so that's enough of the history right now. Now, what Galileo did was Galileo, when shown the instruments with which his entrails would be removed from his scrotum, he decided to recant his argument that the sun was the center of the universe and that all the planets orbiting around it, and just said that the Earth does not move. And for that, he was allowed to live. He was allowed in-house arrest, and it was probably because when he asked to write his book, which I think was called Sidereus Nuncius, part of it was Sidereus Nuncius. When he asked to do that, he asked a cardinal, and the cardinal gave him permission, and then he wrote the book. Well, in the intervening period, that cardinal, who was a personal friend of his, became the Pope. So by this time, the Pope is actually Galileo's close personal friend, but the Pope's advisors were telling him that, Galileo's written this book and he's made a fool of you. And then what he did was Galileo had written this book as a discourse, as a discussion between intelligent people. And the main narrator, if you will, was sort of the person that was asking all the questions. Then one person held the position of Copernicus and Galileo, and then the other person, who they named Simplicio, was the person that held the position of the church. So that's more or less just saying the simpleton. Uh, so that didn't go over so well. That was not a good thing to do. And of course, Galileo knew better. He literally was well aware that Giordano Bruno had just been burned at the stake for something not really so bad. I can't really remember the time frame of Joan of Arc being burned at the stake, but that pretty much happened. So he did that. He was ordered to no longer write, study, or investigate or publish anything about the heavens. And he was sentenced to in-house arrest for the remainder of his life. What he did then was realize that, okay, well, in all the models that he had seen of the universe, we had the heliocentric, which was the Ptolemaic model, or excuse me, the geocentric, which was the Ptolemaic model, and therefore the descendant of, or its descendant was the Aristotelian model and that sort of thing. That was one that the church was still on board with, and largely because Aristotle was sort of the father of science and had given us everything. And not only that, in that intervening period, Christianity became the major religion, at least of that part of the world. And all of biblical scripture was interpreted in terms of the laws of physics or the laws of science. Neither physics nor really the word science was being used that way at that time. But the main thing is the church had adopted Aristotelian thought to explain much of the Bible, and therefore, if you start screwing around with Aristotelian models, you're screwing around with the interpretation of Scripture, and it became a real problem. Uh, we also had the Copernican model, which was Copernicus wrongly said, well, look, we've lost our way from what Aristotle taught us. So he's appealing to authority as opposed to science, as opposed to evidence, reason, logic, that sort of thing. And that was the one thing that Aristotle had, was logic and reason. And he had certain premises that were obvious to him that we would sort of see as Sheldon-esque, if you're familiar with Big Bang Theory and Sheldon from the Big Bang Theory, where, Sheldon repeatedly wears a shirt with the number 73 on it because 73 is the single best number, right? Well, there's literally a principle that Aristotle used, that the heavens are perfect and immutable. Immutable means they can't change. So that literally means to them that something in the heavens can't speed up, because if it's sped up from a speed that's not perfect to a speed that is perfect. And therefore, the heavens at some point was imperfect, or it sped up from a perfect speed to an imperfect speed. And therefore, at the end, the heavens are imperfect again. That's not acceptable. So there was no changing going on in the heavens. And that seemed as obvious to Aristotle and his students as anything else in the world. Also, of course, the heavens are perfect, and the perfect shape is a sphere. Again, very, 73 is the best number type of thing. And in that case, that forced all the orbits to be circular. Specifically, they had to be in a celestial sphere, literally like a crystalline sphere, and then the planet would be embedded in the crystalline sphere, but the rotation of the planet would cause it to move in what's a circle. So, and that's acceptable because it was just a part of a circle. So that was largely what the Ptolemaic model was showing, was the sun at the center, and the earth at the center, and then just outside of it was outside of it was a crystalline sphere that held the moon. Then a bigger outside of that was another crystalline sphere that held Mercury, and then another that held Venus, and then another that held the sun, and then another that held Mars, then Jupiter, then Saturn. That's all we knew of, and that was the Ptolemaic model. And it had a lot of bells and whistles. And in fact, it got so nasty to trying to correct for it, because it turned out to be just so dang wrong, that Kepler once wrote, and Kepler is the extreme pious man. Kepler wrote, if I had been there when God created the universe, I'd ask him to make it a little less complicated, because, Kepler, Brahe, Galileo, Copernicus, these people largely made a lot of their money by writing almanacs, and almanacs would be that's what I'm calling. I'm not sure they really call it that then, but they were books that over the next 10 years would tell you where you could find each of the planets and each of the constellations at any time per year. So their job was to make up these models of the solar system, use those models looking at the past and predict where the planets would be in the future. And that was a really big deal. Does anybody have any idea why governments would pay Galileo or Brahe or Kepler or Copernicus to make such an almanac? Anybody have any reason for that being important to a country, a nation, or whatever? It's me attempting to appeal to your knowledge of history and some of the things you might have learned already. Uh, there, in this time period, this is pre-scientific revolution. In fact, a lot of people say Copernican revolution is a scientific revolution. I don't say that. Copernicus, as I told you, was appealing to authority. He wasn't appealing to the idea of the more modern version of science. However, in that time period, there were other people in addition to Galileo, but Galileo was one of the main ones who was, in fact, appealing to science, experiment, verification on Earth of the things that you predict, and if they didn't go that way, you'd have to throw out the idea that you had that suggested it would go that way. That was, in my opinion, what the real scientific revolution was. And I would call what Copernicus did was the Copernican revolution, where we at least realized that we were a small part of a bigger thing. So if you see those T-shirts with a big spiral galaxy or a barred spiral galaxy on it, and it's got an arrow pointing to this, innocuous little dot, and it says you are here, that's a continuance of the Copernican revolution. Or thinking about the tree of life, which literally is every living thing on planet Earth is a descendant of one common ancestor. And in that sense, we as humans are just one little end of a limb of a tree, along with every other species, including uh, bacteria, fungi, grass, Candida albicans, all that good stuff. So that's what I call a Copernican type revolution, is to realize that we are not necessarily special on the grand scale of the universe, and in fact, we expect the entire universe to behave the same, even in the parts of the universe we're not in. So that's what Galileo brought to the table. Is he brought these experiments and stuff like that. There was a third guy, Tycho Brahe, who had his own model that was quite a bit different, and I'll show you that as well. But what happened was Galileo was sent in for in-house arrest. He had been arguing specifically that the Copernican model was the superior model, and his reasoning was this: uh, Galileo had read by Hans Lippershey that he had created a spyglass, and Lippershey had made this spyglass, but didn't look to the heavens or anything like it. Galileo read how he did it, made it, improved it, made it better, that sort of thing, and then did turn it towards the heavens. Thomas Harriot also did the same thing. He was a physician and scientist on with the group of people that went to what's modern day Manio. Uh, Not the lost colony, but after the lost colony. And it turns out he was there about the same time as Galileo was, and he actually had in his notes where he had also made a telescope and looked at the moon at least. So Thomas Harriot, right here in North Carolina, might have actually beat Galileo to looking at the heavens, but that's only like recently discovered. I heard a particular historical physicist explain that maybe 8 years ago, so it's really fairly new. So Galileo goes to try to make some sense of the universe because he's no longer allowed to study the planets. But what he does know is in these models, all the models have the same thing. They have the fact that Jupiter has satellites. He also saw that Venus had all its phases, and Venus can't have phases in the Ptolemaic model. It can't have all the phases anyway. So that was his conclusive evidence that the Ptolemaic model was wrong. But he was aware of Brahe's model as well. And Brahe's model, I'll show it to you in a little bit with a drawing. is really weird, but you can have all the phases of Venus in that, and he chose to ignore it. So he's a little bit overplaying his hand. That might have been because he was confident that God would not make a universe so aesthetically unpleasing as what Tycho Brahe had come up with, but we're not really sure because he didn't write about it. Uh, so what he did do was toss the idea of of the geocentric model of the universe and went with the heliocentric. And as I said, Galileo had discovered with his telescope that the planet Jupiter had four satellites. He called them the Medicean moons. We now call them the Galilean moons. They're Io, Europa, Ganymede, and Callista Flockhart. Okay, not Callista Flockhart. That's just the wife of Han Solo. But anyways, Callisto was the name of the fourth moon. And one of the ideas of Aristotelian physics at the time was that basically you had four elements: earth, wind, fire, and water. You actually had five if you wanted to count Mila Jovovich. Uh, Again, for the three people in the universe that saw that movie, me being one of them. But the fifth element was supposed to be the heavens, the quintessence. Notice quin is the prefix for the number five, which is quinque. So the quintessence would be the fifth element. The earth, the wind, the fire, and the water would have been the first four elements. And all of his motion was described in terms of those. So there was motion that was called violent motion, and then there was motion called natural motion. So if you had something made of earth, its natural place was to be at the center of the earth. So when you take a earth type thing away from even the surface of the earth, it will naturally move towards the center of the earth and requires no force to sustain that movement. That's natural motion. However, if you were to take that earth like thing, which could have been a rock, and maybe you file it down until it's a nice round ball, if you were to roll that sideways, now that's violent motion because you're not going in the direction that it wants to go. It's not trying to get to the center of the earth. In fact, it's going in a direction perpendicular to that. That is violent motion, and that requires a sustained force. So you've got to constantly push it to keep happening. That's how Aristotle saw physics and how he saw objects falling. And not only that, he saw them like if you had one of those earth-like things that weighed a pound and you dropped it, it would fall at some fixed rate towards the center of the earth. Of course, it gets stopped by the surface of the earth, but it would fall at some rate. Now, if you took a bigger one that was, say, 10 times that weight, it would fall 10 times faster. And that was Aristotelian thought. Another part of Aristotelian thought was if you saw a bird sitting on a tree limb and that bird saw a worm sitting down on the ground, then if the bird were to lift off the tree limb to fly down to get the worm and did so on an earth that was moving around the sun, then the earth would leave the little bird behind. That was just the way they interpreted science of the day. Okay. But by Galileo seeing that Jupiter had these satellites, that was one instance where the bird was not left behind. The four moons kept following around Jupiter for the whole year. So he figured he needed to study motion in general to make sense of that. So that's what he did in house arrest at the ripe old age of 80, which, like I said, he probably only got because the Pope was a good personal friend of his. So, with that in mind, let me open up my iPad and then share it with you. And my iPad is being ultra fast right now. And by that, I mean not at all. Okay, so 241 is the class we're doing. I'm going to take that one. I got this right here. I can delete all that. 241 N02B. Okay. And now we're on February the 5th. Ooh, check us out. 0205. Okay, I'm done there. Now I'm going to go back and duplicate that so I'll have it next time. So now I've got that. Duplicate. Now I'm going to open this up. And now I can do share screen. Look at me remembering to share my screen uh before I turn on my iPad. It's like I'm becoming a real teacher. Oh, speaking of which, can I get you all to go ahead and send me a chat with your first and last name in it, please? That's going to be my roll sheet. Yeah, I'm a real teacher all over the place. So please do send your first and last name in that chat, and that would be super cool of you guys. There I am, finally. All right, it's finally letting me share my screen. Yep, still going. Okay, so first off, I want to show you sort of the Ptolemaic model and what happened with that. So we're going to start down here by drawing the Earth in this itty bitty spot right there. So there's the Earth. Remember, if you actually go outside and look at the stars for a few hours, what you'll see is that there appears to be one star in our northern sky around 30 degrees above the horizon in the northern sky. That sucker looks like it's not moving at all. It's the end of the handle of the Little Dipper. And then you look at the Little Dipper itself, it looks like it's rotating around it in a counterclockwise fashion. And if you look off to the east, you see stars rising and going up and to the right, up and to the right, up and to the right. And then if you look off to the west, you see them going down and to the right, down and to the right. That feels a lot like we're the center of everything and everything's rotating around us. So it's perfectly normal to reach the conclusion that we're at the center. And that's what the Ptolemaic model did. Now, what we had there was Luna, the moon, orbiting around the Earth. And of course, what we know is the Earth rotates in the same direction the moon revolves. Now, outside of that, remember we had these giant crystalline spheres. So you might imagine, for instance, Mercury to be right here, and I'll just write ME there. And then you might imagine, for instance, Venus to be right here. But there's a complication in it. Okay. When you first make this model, it's not that big a deal. But after you've been paying attention to things for a little while, you realize some problems that make it kind of a pain in the butt. So, for instance, what we notice over a period of time is that Mercury never gets very far away from the sun in the sky. Venus does the same thing, but Venus gets further away than does Mercury. So, how would you fix that with a geocentric model of the universe? Well, the ancients did this. They imagined, for no good reason other than it had to fit the data, that there was a line going from the center of the earth and outward till it crossed the what we call the deferent of Mercury, and then further on the deferent of Venus. So this is Venus's deferent. And I'm probably spelling that horribly. And this is Mercury's deferent. Now, if you want it to stay close to the sun, then you're going to have to extend this line just a little further on. And then what we're going to do is put the orbit of the sun. So let me do this. That's our sun right there. So what we're having to imagine is that there's an imaginary line that runs from the center of the earth to the center of the sun. And for some reason, we don't necessarily know why, uh, the center of the epicycle of Mercury and the center of the epicycle of Venus both lie right on that line. So now I have to draw another circle with that green dot as the middle and a bigger circle with that green dot as the middle. Okay. Now imagine they're perfect circles because that would help. Now you can now use this idea to explain that Mercury doesn't get far away from the sun because that little circle won't let it. And you can adjust, of course, the radius of that circle and the radius of the deferent. By the way, this one's called the epicycles. Okay. And on it, you would picture Mercury. And on it, you might picture Venus. Okay. Now, those guys would move around it like this as well as the centers of the epicycles orbiting around. Ooh, I should have put that the other way. Sorry. So we'll say they're all moving this way, this way, this way, this way. Okay. So what you would see is normally day in and day out, you see Mercury going in one particular direction in the sky, like it does on the backside of that circle. But then when Mercury gets right around here, things start to change. You see Mercury's now closer to the Earth, so it'll get brighter. So right about here, it gets brighter, which we can understand because it's closer, and starts to move backwards. Okay, because now it's going to go across the screen from left to right from our perspective, whereas before it was going from right to left. Y'all see that? Now that was a feature, and in fact, that was a feature we needed because the people knew that during that period they called it retrograde. That's what this motion is. During retrograde, everybody knew that the planet would get brighter and that it moved the opposite way. So this circle allowed it, one, Mercury to stay close to the sun, two, it allowed retrograde motion, and three, it allowed the increase in brightness. You know, if things are really going in circles, how else could you explain something going and getting brighter? Because if they're centered on the Earth, they're all the same distance away. The same thing, of course, was true for Venus. So it had a retrograde over here as well. But if you notice by looking at Venus, let me draw this in little black circles. So if we look right here, this half of Venus would be dark. So we'd see a new Venus. If we were here, if Venus was here, again, the half close facing the Earth is completely black. So it'd be a new Venus. If it's over here, then this part would be black and we'd see a crescent. If it was over here, then this part would be black and we'd see a crescent. In fact, we'd never see a gibbous phase. So no full or gibbous phases for Venus. Of course, the same is true for Mercury, but Mercury wasn't easy to see for phases and stuff like that, especially with Galileo's telescope. So he didn't see that. But the main thing is when Galileo saw those phases, he knew this model couldn't work, and he was right. Right. But you can see all the freedom you had. The people that were making these models had the freedom of making the epicycle whatever radius it needed to be. They had the rate at which the planet went around the epicycle was free to be negotiated. The rate at which the sun goes around the Earth, you would set, and that, of course, forced the epicycle to move at a certain rate. So you didn't have that freedom. But lo and behold, back here, you still had Mars, and it had an epicycle on it. And then you had Jupiter, and then you had Saturn. So all of those had those epicycles on it. That gave you a lot of freedom, but you could look back over the data for the last 20 years, make all those corrections. In other words, change the radius of the epicycle, change the radius of the deferent, change the speed of the epicycle around the deferent, change the speed of the planet around the epicycle, all that good stuff. And then, as luck would have it, it turned out the more and more precise they got, the worse things got. So they even had to come over here and define something called an equant point. And that was the point from which you had to look at the planets to see that they were not speeding up or slowing down. Because if you went to the Earth and looked at them, they would appear to speed up and slow down. But if you were at the equant point, they wouldn't. So the Earth wasn't even really the center, but that's what they had to do to correct all that stuff. Okay. Copernicus comes along and again, appealing to authority, says we've lost our way from what Aristotle taught us. Uh, the planets are just a mess. There's 89 cycles within cycles. If you ever watched the movie, what was the movie with the little ants is what it's called, I think. If you ever watched the movie Ants, they were complaining about the main character Flick building tunnels within tunnels. That was them referencing the Copernican revolution, basically, because you got 89 spheres inside of spheres inside of spheres, right? So that's kind of interesting. Well, Copernicus just comes along and says, hey, if I just take the sun and move it, put it at the center, and take the earth and move it and put it out there, all of a sudden I understand exactly why Mercury takes the least time to complete an orbit. I know why Venus is a little longer. I know why Earth is as long as it is. Everything falls into place. But remember, Copernicus is kind of a goober in that he's trying to appeal to authority. So he still will not allow anything other than perfectly circular orbits, and the objects can't speed up or slow down. In the intervening period, Kepler had come along, and Kepler was this. Uh, you can I usually refer to him as Mike Pence, our former vice president. Uh, Not everybody necessarily knows that much about Mike Pence, but a lot of people that know The Simpsons know about Ned Flanders. So you can imagine Kepler as sort of Ned Flanders or Mike Pence, just really straight laced, a good person. Believes 100% in his religion and is not going to deviate from that. But he also had a bit of a problem. He was born, he had like rickets, he had shingles, he had all sorts of crap going on with him. He had piles, he had bow legs, was short sighted, he had a limp, all sorts of stuff was bad with him. He's sort of like Stewart from Big Bang Theory. Okay, but what's worse is his mom was a widower, was widowed, and she lost all her teeth. And I don't know if you know this, but if you pay attention to Western Civ, you'll find out that ladies, God bless them, uh, when they were old and lost their teeth and didn't have a man, they were often convicted of being witches just because they look creepy to people. So that was really a horrible thing, and we did that. And poor Kepler, who was brilliant, had luckily trained to be a priest. He had trained to be a medical doctor. He had trained to be a lawyer. And all of those skills came in handy because one, he was a sickly little dude, so he's always sick. Two, his mom was repeatedly getting called to court for being a witch, and he had to go defend her and that sort of thing. So he really had a sort of bum life, and he was a horrible teacher. He's sort of like me, how I just get sidetracked and talk about Simpsons and stuff like that. Well, just imagine Kepler doing that. He's tutoring kids, and he's got kids that are 6 years old all the way up to 12. And he has this idea why he's teaching them. He's teaching them about the perfect solids, and he realizes that hey, we know there's the sun, we know there's Mercury, Venus, Earth, Mars, Jupiter, Saturn, and that's it, right? And the moon, okay? And it turns out that if you take the number of perfect solids that exist, that's exactly the number you need to separate the sun from Mercury with one shape, and then Mercury from Venus with another shape, and then Venus from Earth with another, and so on and so forth. He said that can't be a coincidence, which by the way, it can. It can totally be a coincidence. Okay. So he decides he's going to start working up this model. I mean, literally with the kids right there paying attention to him. So that's what I meant. He's not a good teacher. Like they're lost. They don't know anything. The parents are paying this dude for nothing. But anyways, he works this out and he immediately sends it to all his friends. So he sends a letter to Galileo, because Galileo and him are contemporaries. He sends one to Tycho Brahe, who's a Dane from Denmark who uh, basically was a bit braggadocious and was brilliant and a really good experimentalist. And he had a silver tongue in that he could talk any royalty into giving him money. So he was really famous. But one day in college, he got in a fight over who was the best mathematician. So he decided to have a duel with us, basically a sword fight over who was the best mathematician. I think he thought he was the best, but he did get his nose cut off in the battle. So now he had a silver and gold prosthetic nose that he stuck on his face with wax, which you can imagine was a pretty hideous looking figure, a poorly sculpted gold and silver nose stuck on a fat face with a big bulgy cheeks and, hair everywhere. And he's sort of the antithesis of Mike Pence slash Ned Flanders. He's Russell Brand, who used to be married to Katy Perry. So think drug addict, sex addict, party animal. That's really what Tycho Brahe is. In addition to being brilliant, and actually, uh, Russell Brand's actually quite smart too. My wife and I read his biography called My Bookie Wookie, and it's pretty obvious he's a bright dude. But the main thing is Brahe's throwing all these parties. He sees this letter from Kepler and he's like, man, I really needs this dude to help me understand and make a model out of my model. So Brahe has his own model. And of course, the model that Copernicus comes up with is basically the sun like this, and then Mercury, and then Venus, and then Earth. Oh, and Mars. Sorry about that. I wrote J. Mars and Jupiter and Saturn, and then the Earth had the little moon going around it as well. That was the heliocentric model of the universe, the Copernican model. But the Copernican model, of course, had only circles and constant speed. Okay, that's Copernicus. Well, the Brahe model, get this. The Brahe model was exactly the same. So you had the sun. So this is Brahe. And we transliterate his name. I think it was transliterating. I'm not sure what alphabet they used at the time, but that's Tycho Brahe, and I think they're supposed to pronounce that Tigo. He's a Dane from Denmark, but his idea was you would have Mercury, Venus. Notice I skipped something. Mars, Jupiter, and then Saturn. Here's the kicker. In Brahe's world, we then had Earth, and this whole thing orbited Earth. So that's the insanity of the Brahe model. So he reads this letter from Kepler and decides, I need that dude because I can't work out the math with this particular model. So he gets there and he realizes Kepler's really a smart dude, and he starts worrying about his historical record. In other words, he realizes that if I bring someone as brilliant as Kepler in here, Kepler might overshadow me with his brilliance and I will be forgotten to history. And as luck would have it, today in my class of 24, two students had heard of Tycho Brahe before. So yeah, that did happen. And in fact, it continued to happen because as I told you, Tycho Brahe is the party animal like Russell Brand. And Kepler is sort of the Mike Pence or Ned Flanders, if you will. And they don't hit it off so well. Kepler's obviously upset that he parties so much. His day basically goes like, I'm going to party, get drunk. I have a pet human. He's got what we would call a little person. That's his pet, if you will. He gets a poor deer so drunk that it falls down the steps, breaks its own neck. Just a horrible, at least from our perspective as modern history, a horrible human. Okay. But he was brilliant. And he didn't have a telescope. He built basically on an island that royalty gave him and told him he could collect the rents and then he could use those rents to build any science equipment that he wanted. And he was a bad landlord. Like he, you can imagine Denmark is like cold like Norway, and he would kick people out in the middle of the winter for not paying their rent no matter what. So he wasn't that cool in that sense either. But he would party till about, midnight, 1 a.m., something like that. Then he'd go out and do observations. And his observations were basically looking through a slot in the wall where there was a big protractor in the opposite side of the room. And that protractor would allow him to get very precise measurements of how high and how far left and right things were. That was his observatory. And he was very good at it. The experimental precision that he got was really good. Like it'd probably take a grad student a year getting used to the modern equipment we have before they could get as good a data as Brahe, and then of course they'd get much better. But still, that was a testament to how good his data was. But as luck would have it, he didn't necessarily give Kepler data as often as he wanted, so Kepler was kind of left in the dark. And then one day, again, as luck would have it, he partied so long. And I don't know if you realize this, like we just heard, poor King Charles evidently has cancer. Royalty largely want us to believe that they don't poop or pee or stuff like that. And that's what Tycho Brahe was trying to make sure everybody was aware of. So he would party all day, drinking beer and eating, buck and eggs and stuff like that, just filling himself up, but would refuse to get up and go to the restroom no matter how bad he had to go. Well, as luck would have it, one day that resulted in his bladder exploding. He became septic and he died a horribly painful death. Uh, Kepler wanted to continue his work. They locked him, his family locked him out. In other words, Brahe's family locked him out. He took them to court, and luckily he won. And the family had the same reservations that Brahe did. Specifically, they were worried about him stealing Brahe's thunder. So Brahe's thunder was ultimately stolen, but to the credit of Kepler, Kepler was able to write an almanac, and he dedicated it to Tycho Brahe because he realized how good Brahe's data was. So at least he was consistent in that. What Kepler did was he looked at those planets and he first tried his own model. His model, though he spent years on it and did a lot of calculations, did not work, so he threw it away. That's what good scientists do. They have to not become so in love with something just because they worked on it. If it doesn't fit the data, you got to throw it out. And that's what he did. He tried the Copernican model. That did not work. He tried Brahe's model. That did not work. So he ultimately had to more or less start over from scratch. And like Copernicus, he realized the heliocentric model was the better model. And ultimately, he was able to conclude that it was the planets sweep out elliptical orbits with the sun at one focal point. We'll get to this later. You don't have to know these now. The planets sweep out equal areas and equal times, and the square of the period is proportional to the cube of the semi-major axis. Those were three epistemological laws, which basically means that they were laws that told how things did, but didn't make any explanation whatsoever as to why they did that. Right? It was just an empty mathematical discovery that he made. It wasn't based on any science that led him to it. But with that being said, you could make a model that worked. And not only that, it worked even when we discovered new planets. So when we discovered Uranus and Neptune and Pluto, we were able to see that they obeyed Kepler's laws of planetary motion as well. So it's bigger than just curve fitting because it was even able to work after things they hadn't seen before, but still it had no underlying theory behind it. That took Kepler, that took Newton to do. So either way, Galileo had learned all this, and then Galileo went in and started studying motion because he had to say, if I want to understand why, for instance, Jupiter has satellites that don't get left behind, I need to understand how those things are not left behind. What he realized is when you drop something, like I dropped this pin, it's going to take off and hit the ground, but it happens so quick you can't tell, does it take off at some fast speed and stay that speed all the way? Does it take off at some fast speed and then slow down? Or does it take off at some slow speed and speed up? And then does it take off at some slow speed, speed up, but then get held back a little bit by air resistance? All that's too hard to tell. But what he realized is if I study inclined planes, I can use basic geometry to relate the ratio of the vertical to the diagonal so that I can figure out what my rate of falling is along the diagonal and how that would compare along the vertical. So what Galileo did was build an incline. And what he discovered is when a ball is rolling up an incline, it slowed down. He let balls go down an incline. And what he discovered was that over time, objects speed up when they're going down an incline. So he made the argument that if an object is rolling along a level surface, that it would neither speed up nor slow down. So, one, he's doing experiments which, Aristotle would have never done. In fact, Aristotle had the idea that, this table I'm sitting at is nice, but it's crap compared to the idea of a table. Because the idea of a table lasts forever. This thing, if I come back in 2,000 years, this desk I'm sitting at is going to be just, sawdust. So not only that, the quintessence was the real and the thing that you can access with your brain, whereas the Earth was a bastardized version of that. And why would you ever do any experiments on Earth? They're a bastardized version of reality. Galileo's not saying that. Galileo's saying, hey, if it doesn't show me how it's going to behave right here, then I'm not going to trust it to behave any other way than it behaves here. And then he went one step further and imagined an infinitely long ramp with no incline whatsoever and imagined what it would do. He also went a bit further and made sort of like half pipes. So he would drop a ball, and what he realized is when he dropped this ball, it would nearly get to the same height on the other side. But he saw it bumping and sliding and stuff like that. So he'd go back and polish it really good. And after he polished it, he found it got a little closer. So he'd go back and polish it a little bit more, and it got a little closer and a little closer. Finally, he reached the conclusion that if I could really get rid of all that force, it probably would always reach back to its initial height. And then he imagined, what if the slope of the other side of the ramp was so low that you would maybe go, 400 light years before you raise an inch? That would suggest that the object lying on a nearly horizontal surface will roll forever. So he's doing experiments and he's imagining the impossible. The impossible is the world with no friction. The impossible is a world in which an inclined plane can be flat and can go on for infinity. And all of that allowed him, one, to define what we know of as velocity, and to define what we know of as acceleration, and to reach the conclusion that balls and objects tended to fall all at the same rate. We don't really understand that yet until we cover Newton's laws of motion, but that's what Galileo gave us. And what he said was, it's as if an object has a certain inertia. That's not an answer to any question. That's just a word that we can stick in there, sort of like what we did with seeing the curve lines of planets and stars orbiting around a galaxy. The velocity that they have doesn't match what we expect from Newton's law of gravity. So it's as if it's a lot more mass inside of the galaxy than we see. So we hypothesize the existence of dark matter. The dark matter doesn't answer the question, right? Until we figure out what the dark matter is, it can't answer the question. But right now, we think it exists and it's causing this. Well, inertia is even worse than that. It doesn't introduce us to anything new other than the word inertia. but it doesn't necessarily explain why. We just can use it to make us feel a little bit better about smacking Aristotle around, maybe. Okay. So that became Galileo's law of inertia. And what he did was basically say an object will tend to keep its motion uniform unless there's a force acting upon it. The way I say it is an object in motion tends to stay in that state of motion unless acted upon by a net external force. You guys are lucky. In the time of Galileo, vectors weren't invented. They came out around somewhere between 1830s and 1870s when Oliver Heaviside and Gibbs from America, Gibbs Free Energy fame, those two guys are the ones that invented vector calculus. So we didn't have it till then. But the main thing is because we have velocity, which is a vector quantity, we can say objects move with constant velocity unless acted upon by a net external force. When I say net, I mean you got to add all the forces acting on it. And when I say external, only the forces that it's not applying to itself apply. So when the net external force on a system is zero, then the velocity will be a constant. That constant can be zero, and that's fine, or it can be like 3 miles per hour at 8.7 degrees east of north. Well, that is Newton's first law of motion. An object in motion tends to stay in that state of motion unless acted upon by a net external force. So that's Newton's first law. I'm not going to write it down. Like I said, I want you guys to copy it from your own book, learn it in those words, and ultimately try to paraphrase it yourself. But be prepared at any time to answer or pick out the actual words that your book used. The second law is the one that Newton is largely completely responsible for. And what he discovered was that in the case where the net force on the system is not zero, then here we go. Newton's second law. In the case where the net force is not zero, and that's the symbol for that I use for net external force. I put that sigma there because sigma starts with S, which is the same thing that summa starts with. So if you're familiar with graduation, the highest honors you can graduate with is summa cum laude, and summa means the sum of all the accolades. And in that sense, we mean the sum of all the forces. Okay. So if the net external force does not equal zero, then the object will accelerate. And I'm going to put a vector symbol on top of that. And that acceleration will be proportional to, remember that little fish symbol there, that's supposed to mean proportional to. What Newton tells us is that acceleration will be directly proportional to the net external force. Directly proportional means thumbs up, thumbs up. If I double the net external force, then I double the acceleration. If I cut the net force down by a factor of 1/9, then I cut the acceleration down by a factor of 1/9. Okay. The other part that he said was that the acceleration is inversely related to the mass of the object. So mass and acceleration are thumbs up, thumbs down. If you double the mass, you cut the acceleration in half. If you cut the mass by a factor of 7, you increase the acceleration by a factor of 7. Okay. Now, if you remember from high school algebra 1 and 2, when they told you something was directly proportional, X is directly proportional to Y, you write Y equal or Y is proportional to X. But then you could change that to an equals by writing Y equals K times X. That's the same thing we do here, only we've chosen to use the K to be 1 in the units we use. So ultimately, what this gives us is the acceleration is equal to 1 over the mass times the net external force. So I want to remind everybody this is the net external force on M. Okay. Now, because I use these vector symbols and now I've got this equals there, we know that when you multiply a vector times a scalar, unless the scalar is negative, it's not going to change direction at all. So this tells you that A is parallel to the net force, and that should make some sense, right? If I push with a great deal of force straight backwards on a person, especially a small kid, you'd expect that small kid to fall backwards. You wouldn't expect them to fall to the right or left or forward, right? So that is Newton's second law, and it's one of the two equations of physics that almost everybody knows, even if they haven't had physics, but it's normally written in this way in the case that everybody knows, F equals ma. But like I said, I always write it with that just to remind you that it's not a particular force is equal to ma. You have to add all the forces on m up to have it equal ma. So that's one version. Maybe y'all can finish this one to prove that there's two equations that almost everybody knows. E equals, y'all know that, right? E equals,
MC squared.
there you go, MC squared. That's the other one. So yeah, those are the two famous equations that almost everybody knows about physics. There's another law of physics that almost everybody knows. See if y'all can finish that. For every action,
There's an equal and opposite reaction.
exactly, and that one's actually called Newton's third law. Newton's third law, for every action, there's an equal but opposite reaction. The way I like to write it is in equation form. So notice the wording that I'm saying here and try to write this down. The force on object A due to object B. Notice how I said that. The force on object A due to object B is equal in magnitude to the force on object B as a result of object A, but opposite in direction. So notice I said equal in magnitude, and I didn't write that negative yet. I just wrote the equals. And then I went back and wrote the negative after I was finished saying it. That's because they're going to point in two opposite directions. And the two things have to be like that, like A to B and then B to A. You can't say the pair of forces from Newton's third law involve the force on you due to the earth and the force on earth due to the car, because you and the earth are the thing. So you'd say the force on you due to the earth and the force on the earth due to you. That's what we mean by Newton's third law. And of course, the force on you due to the earth, does anybody know what that's called? Starts with a W, or a G is another version, but the W is the one I'm looking for. That's the everyday language. It's your W.
Weight.
Yes. I wanted to show you my fat belly, and I figured that would work. Yes, your weight. So the force that the earth pulls on you with is your weight. And it is technically the gravitational force the earth has for you. Now, when you apply, well, let's say me, so we can take the scariness out of the numbers. So when the Earth applies a force of 240 pounds to me in the downward direction, according to Newton's third law, I apply a force to the Earth of 240 pounds in the upward direction. That is a Newton's third law pair. Notice how the two things just switch roles. You can't have three things. You have to have two things, and they switch roles from one side to the other. Okay, that's got to be it. Now, one of the things that this is useful for is, for instance, if you think about hot summer days when mosquitoes and horse flies and whatever those biting flies are at the beach They're always biting you. They suck. So I end up wanting to kill them, even though I'm pretty peaceful and don't wish to kill any living things. Come bite time, I definitely will kill me some flies, right? Well, if you've ever tried to kill a fly, just like out in the air, just by smacking it, you'll see they get a little punch drunk or something. Like you hit them and they're, and then they start flying again normal. So they're straightened up a little bit, but you knock them stupid for a bit. So that's good. But they're clearly going to come back and bite you again when they get a chance, right? So you might wonder why that's the case. Well, the simplest way of saying it, which I say is almost useless, but maybe it comes clear to you. The simplest reason that I cannot kill a fly in the air is that I can only apply a force as big as the force as big as the fly can apply to me. Because Newton's third law says that whatever force I apply to him, he's got to be able to apply it to me in the opposite direction. So just thinking of it that way, that gives you a little bit of an idea. Like, hey, I want to hit this daggone fly with a 250-pound force. You can't do it because the fly can't apply a 250-pound force to you. Now, if you want to go through and think about the motion of how that happens, it makes a little bit more sense. What you can imagine is imagine me being able to throw a fastball at 107 miles per hour. Okay. If I go through my fastball motion like this, and at the peak of my throw, my hand should be moving roughly 107 miles per hour. So if I do my arm exactly like that, and then I smoke a fly in the air, that fly might be moving towards my hand, might be moving away from my hand, might be moving perpendicular to the direction my hand's moving. The main thing is whatever it's moving, it's not going to be moving nearly as fast as 107. So we can pretend like it's moving at 0. Then all that happens is my hand hits the fly and the fly is going to be squished a little bit by the force, but not too much because it doesn't take a huge force to accelerate a fly, right? So I'm going to squish into my finger a little bit, the fly. So the fly's body is going to squish into my fingertips a little bit. And the fly's body is going to get squished a little bit from my fingertips. And over that small of a distance, the fly is going to go from 0 miles per hour to about 107 miles per hour. Now, that acceleration could be quite big because you're going from 0 to 107 miles per hour in a distance on the order of 1.5, 2 millimeters, right? So that acceleration might be big, but look at Newton's second law of motion. Even if that acceleration's big, when you use Newton's second law, you're supposed to use the mass in kilograms. Well, a friggin' fly weighs a few grams. So you're already going to be down by a factor of 1/1000th. So you can see immediately multiplying that itty bitty mass by a fairly big acceleration is going to result in a pretty small force. So that's ultimately also the reason. Yes, the force that you can apply to a fly is limited by the force that a fly can apply to you. But more specifically, if you want to get into the nuts and bolts of it, it doesn't take much of a force to accelerate a fly up to 107 miles per hour. And that's the worst case scenario, which most of us can maybe throw 60 or 70. So does that make sense to everyone? All right. So I've given you that rundown. I will let you know that when I forgot to end that story when Newton said, "If I have seen further than others, because I stood on the shoulders of giants," he said that in the presence of Robert Hooke, who was the president of the Royal Society. But the thing, again, I did mention that Robert Hooke and him were enemies. But what I forgot to mention was that Robert Hooke, in fact, had a bit of a short man's complex. He might have been around 4'9", 4'10". So what he was really saying is if I have seen further than others, it's only because I stood on the shoulders of giants, not stinky little hobbits like you, Robert Hooke. Right. So that's another side to it. And we'll talk more about Newton. He did some weird stuff that you might like staring at the sun for so long that he ended up getting a month-long migraine. That's kind of cool. all sorts of stuff like that. But let me give you just one quick example of Newton's second law. So first off, I want to tell you that in Newton's second law, we've got to figure out what the units of force is, but we know from Newton's second law, it's the same as the units of mass times the units of acceleration. We learned in chapters 2 and 3 that the units of acceleration are meters per second every second, which is really convenient to write that way. So I'm going to write it that way. Okay. What I'll tell you now is that in order for equations in physics to work, the mass that you use has to have units of kilograms. It's not the base unit of the SI technically because it has a prefix, but I'm telling you, any equation that has mass in it, if it's a standard equation that we've derived before, not one for some special lab or something, then you have to use the mass in kilograms or it's not going to work. So if you combine those two, you can see that the unit of force must equal the kilogram times the meter per second squared. And in fact, 1 kilogram meter per second squared is defined to be 1 Newton. And 1 Newton is slightly bigger than 0.25 pounds. Okay. Some books I've read say it's about the mass of a frozen quarter-pound burger, because when it's frozen, it's actually a little bit more than the quarter-pound, right? So that's really more like what the what a Newton is a little bit bigger than a quarter of a pound. I haven't checked that number. I probably should at some point. But anyways, you can just assume that a Newton's around a quarter pound. So now let's imagine a scenario where we're going to solve a physics problem using Newton's second law. The physics problem we're going to solve is I've got this tree and I've been driving a backhoe around and I've scared a big bear. Okay. So now what I have is this cute little bear sitting here like this, just trying to do his own little thing, being all sweet. He's a brown bear. He'd definitely eat you and kill you if he had a chance. Okay. And he's hanging there like that. Got a little bumpy tail right there. And he's hanging like that. And the weight of the bear is in fact going to equal 1,600 newtons. Ooh, really, really big. Of course, that's about 400 pounds. Okay. Now, the mass, which will explain the difference between weight and mass later, but right now I'm going to tell you the mass of the bear is about 160 kilograms. And I will also tell you that the bear is holding on so tightly that he has a friction force of about 400 newtons holding him up in the tree. So what we'd like to know is what is the acceleration of the bear? Okay, this is one-dimensional motion, so I'm dropping the vector symbols. I will tell you that generally speaking, when we solve Newton's laws of motion, especially Newton's second laws of motion, we draw what's called a free body diagram. And that's a diagram that allows us to simplify the problem, usually to the object being like a ball or an infinitesimal ball or a point object. And all the forces are listed on there. And we usually draw a coordinate system. So later, when we learn about things like objects rotating due to torques and stuff like that, we might make the objects bigger and not be point balls and stuff like that anymore. They might actually be arms or squares, and we'll deal with that then. But for right now, I'm going to say this part right here represents the bear. So that's the bear. It has a mass of 160 kilograms, but a mass is not a force. So I'm not going to put that there. I'm just telling you that's what the mass is because F equals ma requires it. Now, the bear would slide down towards the ground if it wasn't for friction. So I'm going to say there is a force acting upward. That's called the friction force, and that's going to be 400 newtons acting upward. There's also a positive force acting downward, and I said that's positive because I'm going to choose down as the positive y direction, like I just did there. Now that force pulling him down, y'all were able to answer this earlier. It's the weight of the bear pulling it down. So that's 1600 newtons, like that. Now here's my test to see if I've gotten all the forces. All the forces that can be applied to something, except for one, has to actually touch the object. So if we're trying to calculate F equals ma, where m is the bear, the only things that matter are the things touching m and then one other thing. Okay. So what we have is the friction between the bear and the tree. So that accounts for the bear touching the tree. We could account for the air touching the tree and take into account air resistance, but I suspect you guys know air resistance be very small compared to 400 newtons of friction. So we don't need that. The only other thing is either it's some kind of force at a distance. So gravity is such a thing. We don't have to physically touch the earth for the earth to pull down on us. So that's one of them that you could put in that spot. Another one would be electric force or a magnetic force or a nuclear force, but that's pretty much it. And in fact, Newton knew the gravitational force was screwed up when he wrote it that way. And in fact, so did Einstein. That's why Einstein came up with the general theory of relativity, because it didn't make any sense that a force like the gravitational force could reach across space without touching something and pull on it. So now that I have all the forces, I can write Newton's second law like this. I can say the net force is equal to mass times acceleration. Again, this is one-dimensional motion, so I don't need to deal with the vectors. Remember, the direction can just be handled by the plus or minus sign. The left side is a summation of forces, so I have to put 1600 newtons. Now it is a summation, so I'm putting this plus in here, but it's probably the only time I'm ever going to put it in here. I'm putting that in there to remind you that I am adding the forces, but the component of the force of friction parallel to the y-axis is in the negative y direction. So I'm going to put negative 400 newtons there. Normally I just write 1600 newtons minus 400 newtons. But you can see that might lead someone to think that sometimes you subtract forces. You never subtract forces. Okay. So that's 160 kilograms times A. So that's Newton's second law filled out. When I do 1600 minus 400, I get 1200 newtons, and I divide both sides by 160 kilograms. And that would give me A. And of course, that means A is equal to 7.5 meters per second every second. Because remember that Newton is a kilogram meter per second per second. So if you divide by kilograms, you just get meters per second per second. Does everybody understand that? The fact that it came out positive tells you that the bear will slide in the positive y direction, which is what we expected. All right, so that's a pretty good introduction to Newton's three laws. Make sure you commit those to memory. Start reading the book. You're going to learn about normal forces. So those are the forces that are perpendicular to surfaces things that are sitting on. So that surface could be an inclined plane, or it might be a table that's level. Those forces have to come into play. In fact, Newton's first law of motion can be looked at as its contrapositive, which its regular statement or if then statement for Newton's first law is if the net force on an object is zero, then the velocity will be a constant. The contrapositive of that is you negate both of those and do it in the opposite order. So I'll say if the velocity is not zero, then the net force is, or excuse me, then the net force is not equal to zero. So that's logically equivalent to the same thing as Newton's first law. So you can use that to reach conclusions when you see something moving with a constant, a non-constant speed. Then you can use that to figure out that there must be a force acting on it. Or if you see something not moving at all, you might be able to conclude, well, there must be two forces acting on it instead of one. That's how we can reason out and get things like the normal force. So you guys can start chapter 4 now. I'm not sure that chapter 4 will be done on Wednesday. So right now we'll probably have chapter 4 set to being done on Sunday. But if I don't finish with chapter 4 on Wednesday, I'll probably move it to the Wednesday thereafter. Okay. Remember, we've only covered chapters 1, 2, 3, and part of 4. So no matter what the dates say, any other chapters are irrelevant. You don't have to do any other chapters, no matter what they're listed on my lab and mastering. So don't worry about dates that come up and pass. I'll fix those later. You guys are free to go. Make sure you send me a chat with your name in it if you didn't already. First and last name. I'm using that for roll. Other than that, you guys are free to go, and I'll wait for the last person to leave in case anybody has any questions.
Thank you. Have a good night.
Thank you. You too, Jacob. Hannah, anybody else have any questions? Caden? Y'all still need the screen, or can I kill that? So any questions? Y'all want me to stop recording or anything so you can ask me a question?
I thought he had a question, but he left.
Oh, gotcha.
I have a